Alright, so far the tests have been pretty straightforward, but what happens is sometimes we have series that don't fit into exactly one of those tests. So here, this is geometric. We're multiplying by 1/2 each time. But this is not geometric. This is a p-series, but if we add 1 here, that's not a p-series. Okay, this we can integrate because we can use u substitution, and du will have an n. This is not easily integrated. So what we're going to use on the front page here is the direct comparison test. Okay. So if we have a list of terms where we know that the term of A is always smaller than the term of B, and B converges, the bigger terms converge, then we know the smaller terms are going to converge also. Okay? And over here, if the smaller terms diverge, then we know the larger terms must diverge. Okay? So that's what we're going to be looking at. If the larger series diverges, we can't tell anything about the smaller one. Okay. So the first thing we want to do is we want to figure out what we're going to compare it to. So here we want to compare this we want to kind of disregard the 5 there and just look at the sum of n equals 1 to infinity of 2n over 3n, or just 2/3 to the n. Like that. Okay? So, if we compare these two, we should see that an is going to be less than bn at all times, because here they're the same, except here we're adding an additional 5 to the denominator. So if you think about it, if this was like 2/3 and this was 2/3, well, this is going to become 2/8 if we're adding 5 here. So 2/8 is going to be less than 2/3. Okay, by adding to the denominator, we make it smaller. So that's less than that. So if we look at this, that's a geometric series, and r is 2/3, and the absolute value of 2/3 is less than 1. So that converges. Therefore, this converges by the direct comparison test. Okay? Alright, so let's try another one here. So this one, let's compare that to just 1 over n to the 1/2. Okay, so here, it says starting at 5, so we could pick something that goes in this a little bit nicer, so we could do a 9. So that's going to be, plug 9 in there, that's 3, that's 1, and that's 1/3. So 1 is greater than 1/3. So this is going to be the bigger one now, and this is going to be the smaller one. Okay, so if we look at this, is so 0 less than 1/2 less than equal to 1. Okay, so that diverges by the p-series test. Okay, so diverges by, oh, I used a lowercase there, the direct comparison test. Okay, so we kind of have that and that and that. I suppose those two could kind of go together. Alright, so let's try that one more time. And looks like maybe you couldn't see some of that under there. So we're comparing those. This one's going to be greater. So here, that's p. P is 1/2. If p is in between 0 and 1, including 1, then it diverges by the p-series test. Since the smaller term, the smaller sequence series, since the smaller series diverges, the larger series must diverge also. Alright. So here, let's compare this to n to infinity. Let's factor out the 1/3. Just have 1 over n squared. We're going to drop that. So if we plug in a 1, we're going to get 1/5 here. And if we plug in a 1 here, we're going to get 1/3. 1/5 is less than 1/3. So this is the bigger one. So we have an is less than bn. Okay, so we've established that. Now here, p equals 2. 2 is greater than 1. So b sub n converges. Right? So since the bigger series converges, then that means this must converge. Therefore, converges by the direct comparison test. Okay, so I think I like this better. Break it into kind of like 3 steps. Figure out what to compare it to, determine which one's bigger and which one's smaller, test that one, and then make your statement about your last one. So three kind of phases there. 1, 2, 3. Here, let's count both of those as 1, 2, and 3. 1, 2, 3. Okay. Alright, so now if we can't find a direct comparison, there's another test called the limit comparison test. So if we're not able to do the direct comparison test, but if we see that the one series is greater than 0 and the other series is greater than 0, if we test the limit of the ratio of those as n approaches infinity, if that approaches a limit that's positive and finite, then both series have to converge or diverge. So if you can set it up and you can find a limit here, and then you can test one of those, then you know that they both are going to do the same thing. So we're going to test the one that we're comparing to, and that'll say that the original is. So that might be a little tricky. It might be easier just to watch one of those. So first of all, this is just practicing what we're going to compare this to. So what you want to focus on is the kind of the highest degree of the numerator and the denominator. So here, that's going to be 1 over root n. Here, this is going to be root n over n squared, or if you bring this kind of cancel, that's the end of the 1/2. That cancels that out. That leaves us with 3/2. And this is just going to be 1 over 2n to the n. So that's just kind of practicing, comparing. Okay, so what we're going to compare this to is 1 over n squared. So this, if we plug in 1, that's 8 minus 4, that's 4, that's positive. We plug in 2, and from there on up, this is going to be positive. So that's greater than 0. Now, if we want to compare that, and this is a little bit tricky. I probably shouldn't write that there because that maybe implies that this, I just didn't want to write it out over again. So I probably should. You got to be careful because the sigma sign there actually is going to mean that I shouldn't do what I was going to try to do there. So 1 over 3n squared minus 4n plus 5, that's greater than 0. And we could take 1 over n squared, that's going to be greater than 0. Okay? So now we can take the limit of this, and so if we're dividing this by this, it's a complex fraction, so we could multiply the numerator and the denominator by n squared, or we can multiply by the reciprocal. So multiply that by n squared. So that would give us this, and these have the same degree, so that's going to be 1/3. So L equals 1/3. So that does have a limit, and both those are greater than 0. So now if we focus on this one, because if either one of these converge, then they both do. Or if either one of these diverge, then they both do. So that's why we compared it to something simple, and we're going to test that. Okay? So n equals 1 to infinity of 1 over n squared converges by the p-series test, because p equals 2 and 2 is greater than 1. So that. So that converges by the limit comparison test. Okay. All right. So let's try that again. So we have n to the k minus 1 over n to the k plus 1. That's going to be greater than 0. As we plug 1, 2, 3, 4, 5 in there, it's always going to be positive. So we want to compare that to something. So how about 1 over n? 1 over n. That's also going to be positive. So now we want to look at the limit. This might get a little bit tricky for you, but So if we multiply both of those by n, if I multiply this by n, if I multiply two things the same base, I add the exponent. So this would be multiplying by n to the first. So I multiply by n and multiply by n. And the numerator's over there. So this is n to the first. So if I add these, multiply these together, then I add the exponent. So that's just going to cancel that out. So that's going to be n to the k over n to the k plus 1. Alright, so if we're plugging in infinity here, this doesn't really matter. Those are the same. That's going to be 1. So the limit equals 1. So we do have a limit, and they're both of these are greater than 0. So the same thing is going to happen to both of these functions. So we're going to test this one out. We do n equals 1 to infinity of 1 over n. That's a p series, so p equals 1, that's to the first power, and 1 is in there, so that diverges by the p series test. Okay, so diverges by the limit comparison test. Okay. All right. Now we have this for starting at 2. 2 squared is 4. 4 minus 2 is 2, so that's greater than 0. Now we're going to compare it to the degree here. So that's going to be 1 over n to the 2/3, which is also greater than 0. Alright? So if we take the limit of that, we have to take the limit to make sure. So that's going to be n to the 2/3. So cube root n squared over n squared minus 2. Alright? So if we think about that at infinity, this isn't going to matter. That's going to be the same thing over the same thing. So that's going to be the cube root of 1, so that's going to be 1. Okay, so both these are greater than 0. The limit of their ratio equals 1. So we can test this one here. Okay, so that's also a p series. So I've been doing that over here. So n equals 1 to infinity of 1 over n to the 2/3. So p equals 2/3. 2/3 is in between 0 and 1, so that diverges by the p series test. So that means, I guess I should have put a 2 there. So n equals 2 to infinity of the other one. Remember, they both do the same thing. So if that diverges, then this diverges also. All right. It's about that time. Have a good day.